In this lesson, we're going to see a variety of ways to represent structures of molecules. We're going to see how we use condensed structural formulas to represent molecules, as well as skeletal structures. Let's look at an example with propane. We know this is an alkane with 3 carbons. The prefix prop tells us 3 carbon atoms. The ane ending tells us that all of the carbons have single bonds between them. And these are all ways to represent the structure of propane. So you can see that in chemistry we have many different ways of representing the exact same molecule. And we use these at different times depending on what we're trying to represent or what information we're trying to show. For example, we call this a Lewis structure, which explicitly shows the atoms and all of the bonding. We have a skeletal structure, which is a pared down version of the molecule that actually only shows the bonds between carbons and the hydrogens are implied. We have the ball and stick model, which represents the atoms as spheres. And then we have the space filling model, which more represents what the molecule actually looks like. Because there are many different ways to show this, it's important to understand what is being represented in each type of structure. Let's start with skeletal structures, which is one of the most common ways that we represent organic compounds. As we've seen before, skeletal structures show us something about the carbons and the way they're attached to each other in a molecule. Because organic molecules can get very big and bulky very quickly, we often use skeletal structures because it simplifies the structure to the essential components. Let's first look at carbon atoms. We see that we have a carbon at the end of the line and at the intersection of each point. And so we can go through and draw in our carbon atoms throughout the structure. So every end of a line and every intersection represents a carbon atom. Now we can go back and add our hydrogen atoms. To do this, we need to remember that every carbon forms 4 bonds, and the hydrogens are what are known as implied hydrogens. They aren't physically shown in the structure, but we know they're there because we know that every carbon has to have 4 bonds. If there are other atoms that are part of those 4 bonds, we would have to show those, but we can leave off the hydrogens when we draw skeletal structures. So the first atom, we see that carbon has only formed 1 bond, so it's going to form 3 bonds to hydrogen. When we look at the next carbon, it already has 2 bonds to other carbon atoms, so it's going to have 2 hydrogen atoms attached. The next carbon has 3 bonds to other carbon atoms, so it will form 1 bond to hydrogen. Next, we have 2 bonds to hydrogen to complete the 4, and then 3 bonds to hydrogen. We also have another carbon that only has 1 bond to another carbon, so we will see that it also has 3 bonds to hydrogen. And now we can see more about this structure, even though what we drew was a very simple model. The formula for this compound would then be C6 because there are 6 carbon atoms, H14 because there are 14 hydrogen atoms. So that will be the chemical formula for this compound. But note that chemical formula doesn't tell us anything about the structure or the way that the atoms are connected to one another. It simply gives the total number of carbon and hydrogen atoms. And in organic compounds, it's also important to know how those atoms are connected because we have many variations on how they can be connected and form different compounds. Let's look at another example of a molecule that has more than carbon and hydrogen atoms. So just like before, we can draw in our carbon atoms at the end and intersection of each line segment. Note that there is no carbon atom at the end of that line because that carbon is bonded directly to the oxygen. So when there's another atom there, there's not a carbon at the end of that line. What we're showing is the bond between the carbon and the oxygen atom. Next, we can look at our hydrogen atoms. So we know the first carbon has 3 hydrogens to make its 4 bonds. Then we have 2 hydrogen atoms, 2 hydrogen atoms, and 2 hydrogen atoms. The oxygen atom will show its hydrogens, so we only add hydrogen atoms to carbon atoms. That's the only place we can have implied hydrogens. Hydrogens attached to an oxygen must be explicitly shown. We can also look at the chemical formula for this compound. So we see we have carbon, and there are 4 of those, hydrogen, which has 10, and oxygen, where there's only 1. Note that I included the hydrogen attached to the oxygen with the rest of the hydrogens in writing the formula. We might also see the formula written as C4H9OH, and this represents that one hydrogen is attached to the oxygen instead of being part of the carbon chain. One thing that sometimes confuses students is how to look at the bonding. So notice that we wrote the O and the H together, but that really means the same thing as if we wrote O with a line representing a bond to hydrogen. Either way is correct, and you will see both of them in various structures. Similarly, we will see that CH3 will be the same as drawing a carbon with 3 hydrogens attached. Both of those mean the exact same thing. Now let's look at a skeletal structure that involves a ring. This is no different than how we would interpret any other skeletal structure. We can start by drawing in our carbon atoms as we go around the ring. As on the previous example, there is no carbon atom between the carbon in the ring and the bromine atom. The bond there represents the carbon-bromine bond. There's also no carbon atom between the carbon and the OH group. Now we can draw in the hydrogens for each carbon atom. Here we have 3 bonds to hydrogen because that carbon only has 1 bond. There are 3 bonds between the next carbon, so it's going to have 1 hydrogen. Then we'll have 2 hydrogens to complete the 4. 1 hydrogen, 1 hydrogen, 2 hydrogens, and 2 hydrogen atoms. Now we see that every carbon has 4 bonds. So we can write the chemical formula as C7, because we have 6 carbons in the ring, plus 1 CH3 group attached to the ring. We have 13 hydrogens attached to the structure, 1 oxygen, and 1 bromine. An important thing to remember is that skeletal structures show us connections between atoms and not anything about the 3D geometry of a molecule. All 4 of the examples shown are for the exact same molecule. Even though the chlorine atoms are shown in slightly different orientations, it is still the same species. If we look, we'll see that we have 2 chlorine atoms attached to the 3rd carbon. And that's going to be true for all 4 of these molecules. So we have 1, 2, 3 carbons with 2 chlorines attached, 1, 2, 3 with 2 chlorines attached, 1, 2, 3 with 2 chlorines attached, and 1, 2, 3 with 2 chlorines attached. On this last example, the molecule is the mirror image, but it still shows 2 chlorines attached to the 3rd carbon in the chain. The important thing is that we recognize how atoms are connected to one another and keep that consistent. Little details of drawing, whether they're both pointing up or pointing down, are not relevant with Lewis structures.